The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so happy to see you again. Welcome back to AO3. So today, as you see on the slides, we are going to continue the discussion of dispersive medium, how the waves and vibration actually are sent through this medium. And also, we will learn about uncertainty principle actually today. Kind of interesting that actually that's connected to what we discussed here. And finally, if we have time, we'll move to two-dimensional system and the three-dimensional system to look at two-dimensional wave and three-dimensional waves. Okay, so that's the plan for today. Just a quick review about what we have learned so far. So last time we discussed about shaking one end of this dispersive medium, which is actually a string with stiffness. And basically, you will see that the strategy what we have been following is to do a Fourier transform to actually decompose the motion of the hand, which is actually holding the one end of the string, and then decompose that into wave population in frequency space. Okay, so that's actually what we have been doing. And then we know, based on the property of this medium, the dispersion relation, which is omega as a function of k, we can propagate, okay? We can propagate waves with different frequency at different speed. Then we can actually see how this system will evolve as a function of time. Okay, so that's actually the whole idea and the strategy we approach this interesting problem. So last time we also introduced N radial, right? So the trick, as we discussed before, if we have a very simple-minded strategy, just send the pulse, which is contain information, directly through this medium. Due to the dispersion relation, which we have this medium, different components will be traveling at different speed. Therefore, the information is smeared out after it travels through a long distance. Okay, so that's a problem, and the solution was to use this approach, which is amplitude modulation method. So basically, and that's actually how AN radial actually works. So basically, we have a slowly oscillating message or signal, like music or voice, which we want to send, and we actually multiply that by a really fastly oscillating cosine term. Okay, if we do this, we're assuming that omega 0 is actually much, much higher or larger than the typical scale of your signal, which is omega s. Then what is going to happen is the following. So after all the calculation we have done last time, we found that the resulting wave, which is actually the amplitude as a function of time and the space psi, okay, you can see that this can factorize into two components. The first component is actually the original signal you are trying to send. It's actually traveling at the speed of group velocity. And finally, the right-hand side, the second component is actually the contribution, or say the really small structure of this high-frequency oscillation. We call it carrier, and the carrier is still traveling at the speed of phase velocity. Okay, so that's actually how we actually finally understand what is actually the meaning of group velocity and the phase velocity through this example. Okay, so what I'm going to do today is to guide you through another example, okay, which actually we can learn some more insights from this calculation. Okay, so today we are going to have another test function, which actually I can do Fourier transforms really easily. And this function I'm trying to introduce here is I have this functional form exponential minus gamma times absolute value of t. Okay? The reason why I choose absolute value of t is because I would like to make it symmetric, okay, around 0. Okay? So this equation, actually I can now do the usual Fourier transform and to extract the wave population as function of angular frequency, c as a function of omega. And according to the formula here, which we introduced last time, we can actually quickly write it down like this. So basically, you get 1 over 2 pi integration from minus to infinity, integrating over time. This is the original function f of t, and multiply that by exponential I omega t. And that's the way we extract a c omega. Okay? And since we have this absolute value here, okay, basically the trick is to actually change the interval, split the interval into 2 pieces, right? So one is actually in the negative t part. Therefore, you get the exponential plus gamma t here. And the other part is actually from 0 to infinity. Then the absolute value doesn't actually change sign. You have the original exponential minus gamma times t. Okay? Then you can actually go ahead and do this integration. Then basically you get the 2 terms, and you get the functional form, which is c omega equal to gamma over pi times gamma squared plus omega squared. Okay? From this simple exercise, there are interesting things which we can learn from here. Okay? So if I go ahead, okay, and draw f of t as a function of time, okay, and this is actually what you will get. Okay? Suppose I have set gamma to be equal to 0.1. Okay, and I would like to visualize this function, and that's actually what we did here. You can see that from the from the left-hand side figure is actually f of t as a function of time, and you can see that this is actually like exponential decay, but symmetric, like mirror at the t equal to 0, right? And with a small gamma value I choose, that means this exponential decay will be really slow, right? Therefore, you have pretty wide distribution as a function of time. Okay. However, if you look at the right-hand side, what is actually in the right-hand side? Right-hand side is c omega. Okay, c as a function of omega. It's the population in frequency space, and you can see that if I plug in gamma equal to 0.1 into that equation, then you get a distribution which is actually pretty narrow, okay, around 0. Okay, so that's actually quite interesting. And now if I change the gamma, I increase the gamma slowly, so change it to 0.2, then you see that, as one expect, the f function within the coordinate space become narrower. But on the other hand, you pay the price that the wave population in the frequency space become wider. Okay, the distribution become wider. I can increase and increase. Now it's gamma equal to 0.5, gamma equal to 1. And now I have a rather large gamma. Now it's at 2.0. And you can see that as a function of gamma, now if I set the gamma to be 5, okay, and you can see that the wave, or say the width of the wave in the coordinate space becomes really small. But if you look at the corresponding c value, c function, you can see that the width becomes really large. Okay, it seems to be telling us something interesting. So it seems to me that I could not choose a gamma value which simultaneously make waves in coordinate space narrow, and also wave population in the frequency space narrow at the same time. Okay, I cannot actually do that based on this simple-minded exercise. Okay, and what you are going to do in your P-set is to go through another parameterization, which is a Gaussian distribution, and basically you will see very similar, hopefully it's very similar conclusion from your exercise. Okay, so what is going on, and how do we interpret this result, and why is this result actually related to uncertainty principle? So that's actually what the first part of the lecture which we are going to discuss today. Okay, so we can actually, of course, demonstrate this effect by one example f of t, which is shown here, right? And we go through and change the width of this distribution. And of course, we can also try to show this in a much more precise mathematical definition. So that's actually what we are going to do now. So the first thing which we would need to do is to define how to quantify the width of the distribution in frequency space and in the coordinate space. Okay, so first, we define that the intensity of the signal is actually proportional to f of t squared. Okay, so that is actually a way to estimate the size of the intensity. It kind of makes sense because, for example, the energy of the electromagnetic wave is actually proportional to the wave function squared, right? So that's kind of reasonable to choose this definition. And then once we have the definition of intensity, then I can now calculate the average of some arbitrary function. For example, I can calculate g of t is the average of the g function. And in this definition of intensity, how to calculate the average is to do an integration over minus infinity to infinity over t. And this g function is put there. And all the components are weighted by this intensity estimator, which is actually f of t squared. Okay? Of course, since we are actually calculating the average, we need to take out the sum of the intensity, right? So the sum of all the intensity is the integration from minus infinity to infinity dt f of t squared. Okay? With this definition, we can actually calculate the average. Okay? And don't forget, our goal is to have an estimator estimate the width of some distribution, right? So therefore, you are probably very familiar with that. We use standard deviation, right? So basically, that's also usually associated with this exam, but this time it's actually associated with some physical quantity, okay? So what is actually the estimator of spread of time, right? We can actually make use of this definition, and I can use this notation delta t squared to be a quantity which is associated with the size of spread in time. And that is actually defined to be the average of t minus average of t squared. So basically, you calculate the difference with respect to the mean value, square it, and I do then the two average again. Okay? All right, everybody is following? Any questions? Okay. So if I have this standard, so-called this standard deviation or spread of time definition here, then I can write it down explicitly, and this will become minus infinity to infinity to this integration over t And I have t minus mean value of t, f of t squared. And of course, I will take out the normalization, which is minus infinity to infinity dt ft squared. OK? And I can also do a similar exercise for the frequency space, right? So basically, I can define the spread of the frequency spectrum. And that I define it to be delta omega squared. And this will be defined as the average of omega minus the mean value of omega squared. OK? And with this definition, in our hand, we have an estimator of the spread of time. And we have an estimator of spread of the frequency. And the phenomena which we see from here, from this exercise, going from low gamma value to large gamma value, is that it seems to us that the spread of the time, or in coordinate space, and the spread of the distribution in the frequency space cannot simultaneously be small. OK? Therefore, based on this mathematical definition, our goal is now to show that, OK, we can actually prove that delta omega times delta t will be larger or equal to 1 over 2. So that is actually an interesting consequence. Based on this definition of spread, etc., we can actually achieve from the lecture today. So that's our goal. And we are going to try to actually achieve this goal. Before we actually go ahead and prove this relation, delta omega times delta t greater or equal to 1 over 2, we also realize that when we discuss the spread of the frequency spectra, OK? If I write it down here, basically, if I try to calculate the average of omega, OK, then basically what I'm going to do is to do an integration from minus infinity to infinity d omega, right? Because now I'm trying to calculate the mean value of omega. And I have the omega times c omega, OK? And the exponential minus I omega t. And this is actually OK. So if I actually go ahead and evaluate this integral, OK? Basically, I integrate over omega, and I have omega times c omega times exponential I omega t, OK? And you can see that this omega can actually be extracted from this exponential function. If I do differentiation with respect to time, then I can actually extract 1 omega out of the exponential function, right? Therefore, what I'm going to get is this will be equal to 1 I partial t minus infinity to infinity d omega c omega exponential minus I omega t, right? So you can see that this is actually the design. If I do a partial derivative with respect to t, then I take minus I omega out of this exponential function, right? And this I will make minus I become 1, right? Therefore, you can see that this integral which I construct is actually equal to I partial t this function, okay? And you can actually quickly realize that, this is actually, we know what this integral is doing, right? According to the formula which I listed here, f of t is equal to this integral, which I actually just highlight there. Therefore, this is actually just f of t. Okay, so that's actually kind of interesting because that will give me I partial t f of t. Okay, so basically you can see that I don't need to deal with omega. I can actually do a partial derivative with respect to time. Then I can actually take 1 omega out of that function which I construct. Okay, any questions? All right, so now I can calculate what will be the mean omega. Okay, what would be the mean omega? The mean omega, according to this definition here, okay, this is actually how we actually calculate the mean of some quantity. Okay, mean omega will be equal to minus infinity to infinity dt f star t I partial t f of t. Okay, sorry, this is actually kind of close to here. Okay, so originally, the original definition, I should put omega here, right? But instead of putting omega there, I use the trick that this I times partial t can generate an omega for me. Okay? Therefore, instead of putting omega explicitly into the integral, I put I partial t into the integral. Then I get 1 omega out of it. And that's actually equivalent to the calculation with g of t equal to omega. Okay, everybody is following? Okay. Therefore, I of course still need to normalize the calculation, right? So this is actually give you the denominator, which is actually minus infinity to infinity integral over dt f of t squared. Okay, so you can see that instead of using omega directly, I use this trick to use I partial t to extract 1 omega, and I can actually calculate the mean value of omega. Therefore, I can also calculate explicitly what would be the delta omega squared. Based on the definition which I outlined before, this will be the average value of omega minus mean omega. Mean omega is actually a number. And if I write it down explicitly, basically I get minus infinity to infinity dt I partial t minus average value of omega f of t squared divided by minus infinity to infinity this integration over dt f of t squared. So the take-home message is that I'm using this trick to replace all the omega by I partial t. Therefore, in my formula, you'll see that originally this is actually supposed to be omega, and that is actually we were using that trick. Therefore, it can be written as I partial t, and you will realize why this is actually useful afterward. Okay. All right. So those are just preparation, right? So what have we been done is that my goal is to show that delta omega times delta t is greater than or equal to 1 over 2. Okay, so that's my goal. And I'm preparing for that. And I have the definition of delta t and delta omega. Yes?
What are you taking the partial over?
Sorry. So there should be, it should be like this. So I'm taking partial t out of f. Okay, sorry, very good question. Okay, any other mistakes? Very good. All right, not yet. All right, so now you can see that I have the definition in my hand. And I'm almost there to show you that delta omega times delta t is going to be greater than or equal to 1 over 2. Okay? And what I'm going to do after this, maybe you will be even more mad at me, is to use exactly the same trick which will be used to show Heisenberg uncertainty principle in quantum mechanics. Okay? So basically what I'm going to do is to consider a function which is r of t. Okay? It's actually r of as a function of kappa and t. Okay? And the definition of this r function is like this. I define this r function to be t minus average t minus I kappa I partial t minus omega f of t. If you don't know why this is, where this is this relation actually coming from, don't be worried because you don't really need to. Okay, this is actually just to guide us through this mathematical calculation. Okay, but if you can see directly that this will help, then maybe you are Heisenberg. Maybe. Okay, so that's very nice. It's a test. Okay. So what I'm going to do is to employ this r is a function of kappa and t, okay, and for our purpose to show that delta omega and delta t greater than 1 over 2. And first, to make my life easier, I will define this to be capital T, and I will define this thing to be capital omega. Okay, so that my mathematical expression doesn't explode. All right? So now I can consider this ratio function, r of kappa. This is defined as minus infinity to infinity integrating over t, r kappa t, divided by minus infinity to infinity dt f of t squared. Okay, this is actually the r function, which is the ratio of the area of gamma of r function and the area of the f function. Okay, you may say that Professor Lee is really crazy today, is telling about all the crazy things, but that's actually because I would like to let you know that we are going to see a very interesting result. So that's actually why I'm doing this, okay? And if I construct this r function, okay, this r function have an interesting property. What is the interesting property? I'm doing integral over something squared in the numerator and the denominator, okay? That means what will be the value of this r function? The r function will be always positive, right? Because this is squared, this is squared, therefore r is going to be positive, right? So that means r is going to be greater than or equal to 0. Okay, so that's actually why we have this r function. And the miracle will happen because if I go ahead and calculate this r, okay, before I calculate this capital R function as a function of kappa, I need to actually deal with this small r as a function of kappa and t squared, right? So if I extract this component and calculate that, r kappa t squared, okay? Basically, what I'm going to do is to use this expression, right? R is actually now equal to t, capital T minus I kappa omega times f of t, right? So that my life will be easier. Then basically you get t minus I kappa omega f, right? And you need the complex conjugate, right? Basically, you get T plus I kappa omega star F star. Okay? You can have T star, but T is actually a real number. Therefore, it doesn't do anything. Okay? Then I can now go ahead and collect all the terms. Then the first term which I can collect is everything related to T times F. Then basically you get TF squared. Okay? So that is actually coming from this T times F times T times F. This term times this term times this term times this term. Okay? Giving you the first term. And also you can collect another term which is actually omega F squared. Right? So basically you can actually find that contribution. Okay? Okay, you should have a kappa square in front of it. Right? Any questions so far? Basically, I collect the terms related to omega times F and put it here. Okay? Then finally, you have the third term, which is I kappa TF omega star F star minus omega F T F star. Okay, so basically this R, a small r function squared can be written in this functional form. Okay, we are almost there. So what I'm going to discuss first is that, okay, now I have these three terms. Number 1, number 2, and number 3. Okay, so I can now attack number 3 first. Number 3, I'm going to get I kappa TF minus I partial T minus omega F star. Right? Basically, what I'm doing is to take this omega here. This is omega star. Okay, and use the definition. Basically, write down the expression for omega, capital omega explicitly. Okay, since I'm writing omega star, therefore you get the minus I partial T minus average omega out of it. Okay, so that's actually why here you have this expression, and then multiplied by F, which is the original expression. Okay, minus, I also write this omega, capital omega explicitly, I partial T minus average omega, okay, F T F star. Okay? And you can immediately realize that, okay, the whole thing is actually multiplied by I times kappa, right? So you can immediately recognize that this term actually cancel, right? Because they are really the same. And then what is actually left over is the two terms, which is in the middle. So basically, what you are going to get, now I can actually multiply I and put it and cancel this minus I, right? So basically, what you get is kappa times T, because both terms have a T, right? So I can extract this T out of it. Okay. F partial F star partial T plus partial F partial T F star. After all those works, you can see that, this one looks pretty nice, right? This is actually what? This is not bad at all. After all those calculations, after all those cancellation, basically, this will be equal to kappa t partial t f star. Okay? Everybody is following, or everybody already lost? We are almost there. Okay? All right. So now we have these three. Three originally is a beast. Looks really horrible. And after I write it down explicitly, it looks okay. Not perfect. Yes? F star is actually the complex conjugate of the f function. All right? So now I can put 1, 2, and 3 into this integral, right? Then we are done. Okay? So now let's put number 3 into the integral first. I do a minus infinity to infinity number 3 dt. Okay? So what is going to happen? This will give you minus infinity to infinity kappa t partial t f star, right? And I can use integration by part, right? So basically, what I'm going to get is kappa t f star, integrating from evaluative at minus infinity and the plus infinity, minus kappa minus infinity to infinity f squared partial t partial capital T partial t dt. Okay, let's look at this. So basically, what I'm doing is to put in the number 3 term back into this integral. Okay, and use integration by part, right? So basically, you can see that this is actually what you would expect. Okay. The interesting thing is that this function is evaluated at plus infinity and minus infinity. Okay. If you assume that your f function is localized, okay, it's confined in some specific range of time. Okay, instead of spreading out over the whole universe. Okay, that means this term will be equal to 0, right? Because it's evaluated at plus infinity time and the minus infinity time. Okay? If the f function is localized, then at the boundary of time, you are going to get 0. Okay? So this term disappears. Very good. We solved one problem. Okay? And this looks horrible, but partial capital T, partial t, what is actually capital T? T is actually small t minus average t. Average t is a number, and t is just t, right? Therefore, partial t, partial small t is actually just 1. Okay, you can see that there are hopes, right? So things are becoming simpler and simpler. Therefore, what I'm going to get is this, minus kappa minus infinity to infinity dt f squared. Okay? And if you divide this, if you actually divide that by this term, okay, basically you can see that number 3 term will give you a contribution of minus kappa. That's all. Because once you plug this integral back into this R function, the third term contribution gives you minus kappa. That's a very good news because it's actually pretty simple. Any questions so far?
Same a dt.
Oh, you mean this one?
No, the one to the left of that.
This one?
No, to the left.
Oh, to the, yeah, you are right. I missed a dt. Thank you very much. Very good. Yeah, so basically what I'm trying to do is plug in the expression here into that integral, and yeah, you are right. Thank you. Okay, so you can see that the contribution from the third term, number 3, is rather simple. It's just minus kappa. And that's actually also take a look at the contribution from the first and the second. Number 1 basically will give you minus infinity to infinity, t minus every t squared f of t squared t. And this is divided by minus infinity to infinity dt f of t. This is actually not crazy at all, because this is actually just the definition of delta t squared. Just a reminder that the definition of delta t squared is written here, okay? Therefore, this is actually just delta t squared, the first term, which looks really strange there, but in reality, it's actually very simple. Let's look at the second term. It's actually kappa squared minus infinity to infinity I partial t minus average omega. Okay, f of t, and square that. Divided by minus infinity to infinity dt f of t squared. Okay, and now we'll give you kappa squared delta omega squared. Okay? Basically, our conclusion is that this R function is a function of kappa is actually equal to the first term is here, delta t squared. The second term is plus kappa squared or delta omega squared. And finally, the third term is here, right? Minus kappa. And then minus kappa. Okay? And this will be greater or equal to 0. Right? Because what I'm doing is actually summing all those positive functions. Okay? And take the ratio. Okay? Any questions?
Yeah. Why does the integral from negative infinity to dt f squared equal 1?
Oh, this one? Oh, this one.
Yeah, the one underneath.
Oh, this is actually equal to 0, right? Oh, here.
Yeah. Why does that? Why does?
I see. I see your point. So this is actually integrate minus infinity to infinity number 3 dt. It's the contribution here. Then if I take a ratio between this term and that term, then this is actually canceled by the denominator. Therefore, what is actually left over is minus kappa. Okay, so these the contribution of 3 in green is actually already taking the ratio when I evaluate the capital R function. Okay, good question. All right, so now you can see that basically you can safely ignore what I have said so far. Everything you can ignore, those are just mathematics tricks, okay? But what is actually important is that now I have this relation, delta t squared plus kappa squared delta omega squared minus k. Okay, this is a function of k. And I can actually minimize it. I can minimize R by carefully choose a kappa value, right? So this kappa equal to kappa mean value, okay, which makes minimize the R function is actually equal to 1 over 2 delta omega squared, which I will not go over this calculation because this is actually just a minimization problem, okay? So that means if I plug that in, what I'm getting is that R kappa mean will be equal to delta t squared minus 1 over 4 delta omega squared. That is greater or equal to 0. Okay? So we arrived there. if I multiply both sides by 4 delta omega squared, basically you get delta t squared delta omega squared greater or equal to 1 over 4. If you take a square root of that, then basically you get delta t delta omega greater or equal to 1 over 2. That's actually what we actually started to try to prove, right? So basically, you can see that after all those works, a lot of complicated mathematical calculations, you can see that we actually make no assumption. We are just using the definition of the spread of time and the spread of frequency. We follow that definition and use a mathematical trick which were used to prove Heisenberg's uncertainty principle. And we arrive there. This means that this is actually an intrinsic property of wave function. Intrinsic property means it's a mathematical property of wave function. Okay? So what do I mean by this equation which we actually finally derive? So after all those hard work, we have to enjoy, right, what we have learned, right, from all those craziness, right? So what do we learn? So look at this function. Delta t times delta omega greater or equal to 1 over 2. That means if I construct, okay, a f function, which is actually how I oscillate the string as a function of time. If I construct a really narrow one, do this, very, very fast, okay, then I stop. Okay, very narrow. Then you will have a very small delta t. Okay, that sounds really nice. I produce a delta function in delta t, but the delta omega space is going to be in a mass. It's going to be a super wide distribution because delta t is really very, very small. That means you have to compensate that by a rather large delta omega because if you multiply delta t times delta omega, that is going to be greater or equal to 1 over 2. Okay? And what is actually the consequence of this, for example, for the discussion of AM radio? Okay? If I have an AM radio with bandwidth means delta omega. Okay, this is actually 2 pi delta nu. And that is actually roughly something like 3 times 10 to the 4 hertz. Okay, so if I have some kind of bandwidth, which is actually roughly this band, okay, so I can now immediately calculate what will be the resulting delta t. The resulting delta t will be a few times 10 to the minus 5 seconds. Okay, based on this equation. Okay, so this means that if I'm trying to send 2 signals, okay, in sequence, if I try to send 2 signals in sequence through this AM radio, that means if the delta t, the time difference between the first and the second information, if the time difference is large, if the delta t between these two is larger, much larger than 10 to the minus 5 seconds, then I can actually easily separate these 2 signals. Okay? On the other hand, if I send then really the 2 signals really close to each other, it will look like this. Then the receiver, the ones who receive the signal, will not be able to separate if this is actually 1 signal or 2 signals. or 1 pulse or 2 pulse, which you are trying to send. Okay? Any questions so far? So you can see that we can actually quantify what will be the limitation in the resolution, time resolution, okay, due to the limitation of bandwidth, delta omega. Okay? Before we take a break, I would like to make connection to quantum physics. So if I look at this delta t times delta omega greater than or equal to 1/2, this expression, I can rewrite it. I can multiply t by velocity v, and I get v times velocity. And I can have omega divided by v, okay? And this will be greater or equal to 1/2. So I just multiply v and divide by v. They actually cancel, okay? And that means this will become delta x. And that, the second term will become delta k. And that will be greater or equal to 1/2. Okay? In the quantum physics, momentum is equal to h bar times k. Momentum will be equal to h bar times k. And h bar is actually Planck's constant. Okay? So that actually you will see that a few times in L4. Okay? So if I have P equal to h bar times k, that means I have delta x times delta p greater or equal to h bar over 2. That is exactly the uncertainty principle which is actually introduced by Heisenberg. And what is actually the meaning of this? So if we describe all those particles we see by quantum mechanical waves, okay? If I have momentum p, that will correspond to a wave function with wave number k, and the constant which associates p and the k is the Planck constant. Okay? So this means that if I measure one particle really, really precisely in a position, okay, due to the nature of wave function, that means I will not have a lot of information about the momentum of that particle. And where this uncertainty principle coming from is coming from purely the mathematics related to waves. Right? As you can see there, there's really nothing to do with quantum so far. And the quantum thing actually only goes in after we prove the uncertainty principle, delta omega times delta t. You cannot have a very precise angular frequency and a very precise position in the coordinate space or time at the same time. And that actually have direct consequence. That means if you are considering quantum mechanics, that is actually the limitation which will be posted, the uncertainty principle. Okay? So we will take a 5-minute break, and we come back and we will take a look at 2, 3-dimensional waves. And let me know if you have any questions. Okay, so welcome back, everybody. So before we actually move to 2, 3-dimensional waves, we will discuss a very interesting topic which is related to the dispersion relation of the light, actually. Okay, so if you use special relativity, basically you have you can relate energy to momentum and the mass, right? So E squared will be equal to P squared C squared plus N squared C to the 4, right? And if you have, you actually interpret light as a photon, then basically E is actually equal to, the energy of the photon will be equal to h bar times omega, okay? So we are actually really going really forward a bit because maybe some of you actually haven't seen this before, but if you just believe what I have said, okay, basically you can actually divide everything from the first formula, which is the special relativity formula, by h bar squared. Then you will be able to derive and arrive the second formula, which is omega squared equal to c squared k squared plus omega 0 squared. Okay? And the omega 0 is actually defined as nc squared over h bar, just for simplicity. Okay? So if you look at this equation, okay, this is actually a dispersion relation, right? Now you have seen this so many times, and this omega squared equal to c squared k squared plus omega 0 squared. This formula is actually reminding you that this is actually a dispersion relation. Okay? So what does that mean by photon having mass here? Okay? That means the m term in this special relativity formula is non-zero. Okay? Therefore, omega 0 will be non-zero. What is going to happen? That means the space velocity of light is going to be different. It depends on what value of k you choose. Okay, that's kind of interesting, right? Because that means light with different frequency or different wavelengths is going to be traveling through the vacuum at different speed, if that's true. Everybody get it? Very cool. So how do we actually test this? Right? So that means I need a light source which are very, very far away from Earth. Then I would like to measure the delta t as a function of frequency, for example, and energizing. Okay? So how do we do that? So this is actually possible if you actually use a natural light source, which is the pulsar. So what is actually a pulsar? So what we actually use is actually a millisecond pulsar. So those are actually coming from rapidly rotating neutron stars. And those rotating neutron stars will emit pulsar radiation like X-ray and radio waves at a regular interval because it's actually rotating again and again. Okay? Based on this movie, basically what is showing here is a very old neutron star. It's actually in a binary system. And this neutron star can absorb the material from the other partner. So that actually is the rotation speed actually increase. And finally at the speed of millisecond per turn. Okay? So this actually really happened, and we can actually observe this. And if we are lucky, okay, the Earth is actually somehow in a spatial direction such that the emitted radio wave actually pointing from the pulsar to Earth, then I can see the pulsar, the amplitude of the light from pulsar is actually changing rapidly as a function of time. And another very good news is that typically those pulsars are really far away. For example, in this example, pulsar B 1937 plus 21, this is actually a pulsar with rotation period of just 1.6 millisecond, okay? And this is actually something which is really happening really far away from the Earth, which is actually 16,000 light year away. Okay, and we can actually observe this. This is actually pretty close to Sagitta, and you can actually see this pulsar. And how does that actually associate with the original question we were posting? The original question is, does the light with different frequency travel at different speed? right? And this is actually a very nice tool, right? Because it's emitting the radio wave, and then now I can just measure the spectra as a function of time. Then I will be able to see if we actually can observe different speed, because we know the rotation interval and etc. And we also emit the wide spectra of the frequency, the light frequency. Therefore, I can use this as a light source far, far away from the Earth to see what will happen. Okay? So somebody actually did this measurement, and this is actually what they found. They found a non-zero omega zero was found. So that means the mass will be 1.3 times 10 to the minus 49 gram. That sounds really small, but it's not small at all. That's actually destroying the whole understanding of light. Right? What is going on? So we are in trouble, right? So after all this discussion, etc., and also other measurements which are sensitive to photon mass, they actually rule out this possible contribution. This is actually just simply too large, based on, for example, measurement of magnetic field in the galaxy, etc. It doesn't really work. So what is actually really happening? The explanation is that the path from the pulsar to the Earth is really not vacuum. There are very few or very dilute electrons, very dilute free electrons all over the place. And that will change the frequency and the speed of light slightly. Therefore, you see the interesting observed effect. And we are going to actually also talk about how the material actually change the behavior of the electromagnetic wave in the coming lectures. Okay, I hope you find this interesting. Any questions? All right. So we are going to move on. So far, what we have been discussing is always one-dimensional waves, right? So for example, string, we also, and also the sound wave in the tube, etc. We always discuss things which is in one dimension, okay? But we are actually not one-dimensional animal, right? We are three-dimensional. And of course, those, for example, this object, the surface is two-dimensional, right? So there are many, many things that are more than one dimension, okay? So the question I'm trying to ask is, can we actually understand this kind of object, and how actually to understand those objects, and how do we actually derive the normal modes, and how do we actually write down the general solution, which describe two-dimensional or three-dimensional wave. That's actually the next topic which I would like to discuss. So that's actually get started with a plate like this, okay? So basically, that plate can be is actually a two-dimensional, okay? And I assuming that this plate is infinitely long, okay, for the moment, okay, very, very long, okay. So what does that mean? This means that if I define my x and y coordinate, okay, which is actually used to describe the position of a specific point on this plate, okay, then basically you'll see that there are beautiful symmetries which you can actually identify from this simple example. What is actually the symmetry which you can identify? Can anybody help me with that? Yeah, so yeah, x and y are symmetric, yes. And as a function of x, what kind of symmetry do you have? Reflection. Yeah, also refraction. And what I'm looking for is if I change x and change y, what kind of symmetry do you have? Translation symmetry. Well, all of you are correct, right? But what I'm trying to focus on now is the translation symmetry, right? So if I use translation symmetry, what I'm going to get is that I can already know the functional form of the normal mode, right? Because it's actually, if it's translation symmetric as a function of x, it's translation symmetric as a function of y, then the eigenstate is in the x direction will be proportional to exponential ikx x. K underscore x is actually the wave number associated with the wave in the x direction, right? So that's actually one consequence which we actually learned from the discussion of symmetry. And in the y direction, I can conclude also that the normal mode will be proportional to exponential iky times y. Okay? Therefore, I already know what will be the functional form of the normal mode of this highly symmetric system. Okay? What is that? The psi xy will be equal to a times exponential ikx times x exponential iky y. Okay? So you can see that if I, and also I need to take the real part, right? Something like this will be a possible normal mode, okay? Therefore, without going into detail, basically, we'll see that the expected behavior of psi as a function of x and y will be like something like a sine kx times x sine ky times y. Okay, so that's actually the kind of normal mode which we will expect based on the argument of translation symmetry. Okay, and of course, if I now go back from infinitely long system, okay, to a finite system, then you can actually use the boundary condition to determine what will be the k value, kx value, and the k value, allowed kx value and allowed ky value using boundary conditions. Okay, so actually without doing any calculation, we can already find that, okay, so now if I have a plate with finite size, okay, basically you expect that, okay, I can have some kind of normal mode, which this is an amplitude projection in the x direction. It can be a sine function, and it can become 0 at the left-hand side edge and the right-hand side edge. And in the y direction, it has to be also some kind of sine form, some kind of sine wave as a function of y, and of course it goes to 0 at the edge, because if those are actually the fixed boundary, for example. Okay, and if those are actually not fixed boundary, then you expect that, okay, like open-end solution. So you expect that the distribution will be more like a cosine function, right, for the first normal mode. Okay, and if you look at this, the structure of this kind of solution, it looks really complicated because you have x direction and you also have y direction. Both of them are actually sine function. Okay, and how do we actually visualize this kind of sine function? And here is actually a demonstration which I prepared. It's really a two-dimensional plate, and you can see that under this plate I have a loudspeaker which actually produce a sound wave to try to excite one of the normal mode. And what I'm going to do is to turn on this loudspeaker. You can hear the sound, and I would like to see the normal mode. But it's very hard to see that, right, without doing anything, because, okay, it's vibrating, but it's so fast and it's really, really difficult to see it. So what I'm going to do is to pour some of the sand on the surface and see what is going to happen. And if you look at this, I'm putting sand on it. You can see that there's something happening. If I change the frequency to one of the normal mode frequency, you can see that now we are reaching some kind of resonance. I'm exciting one of the normal mode. And you can see that the sand actually doesn't like to stay on some of the place because it's vibrating like crazy and it's not very comfortable to sit there, right? So the sand, where will the sand actually sit? They will sit at the place where you don't have any vibration. Because what we are looking at is actually some kind of sine wave times sine wave or cosine wave times cosine wave. That means there will be nodes, right, on the plate, and those are two-dimensional nodes. In the one-dimensional case, we are talking about nodes. It's actually the place where you have zero amplitude. And now I have cosine times cosine. Therefore, there will be complicated pattern appearing, which is actually the plate is not actually moving at all as a function of time. And you can see that, now I can actually excite one with the normal mode, and you can see really beautiful pattern. And let me do this and increase the frequency so that to see if I can excite another normal mode. Look at what is happening. So now you can see that the number of lines actually increased, right? So this is actually so-called figures. Basically, those figures are actually produced by this kind of trying to excite one of the normal mode, and basically the sand will be collected in the nodal lines, and you can see that in this higher frequency input sound wave, you can excite the higher frequency normal mode, and then, of course I can continue to increase and see what happens. Now I'm increasing the frequency even higher and higher. You can see that now the sound is actually rather loud, and I am actually putting more sand. You can see that there are more and more patterns, right? Because now I am increasing the frequency so that actually higher frequency normal modes are excited, and you will expect more notes, right, for higher frequency ones. And now I can even go even higher to see if I success. It's not easy now. Look. Probably this is a very good way to design the pattern of your t-shirt. Okay, so how do we actually understand all those patterns? And we have already started that this is actually something related to cosine and sine multiply to each other. And the next time we are going to do a more detailed calculation and show you a few more demos and see if what we can actually learn from the two-dimensional case. Thank you very much. I hope you enjoyed the lecture today. And if you have any questions, let me know. And you can actually come forward and play with those demos if you want.